Thomas is ready. We are almost ready.
I hope the audience is ready.
We hope the audience is
ready to go.
So now, Thomas to give this fourth and last lecture for the week. Let's go.
Yeah, thank you very much. Last time we proved that K-theory of a ring was a K-theory of a commutative ring was a spectral lambda ring, which in particular implied that the homotopy groups of K-theory were lambda rings in the classical sense, and by this I always mean special lambda rings, by the way, in the old nomenclature. And then we proved, one of the key things to understand these spectral lambda rings was to understand the K-theory of the strict polynomial functor. I guess this is Broch-Z. And somehow, yesterday I was a little confused why this is an E-infinity ring, but this is of course clear because it's the first mapping space in the algebraic theory, hence the free spectral lambda ring on a single generator. We had already said that every spectral lambda ring in particular has an underlying E-infinity ring. Just got a little bit confused when Stefan asked that yesterday. And so we don't know really what this is as a ring spectrum. We know underlying it's the direct sum of KZs, and the homotopy groups look like this polynomial ring on the elementary symmetric polynomials. We don't know what it is as a ring spectrum. For example, it's not the flat ring spectrum, if you wonder about that. That one can prove, and in the end I defined for what a Wildhausen infinity category is and how to get a K-theory spectrum out of a Wildhausen infinity category. And let me start with a little construction today. So I'm in the situation of a Wildhausen infinity category, and the claim is that there's a canonical map from the underlying space of the Wildhausen infinity category into the underlying space of the K-theory spectrum. And this is a map of E-infinity monoids. And how do you get that? Well, you just can see that by writing down what the things look like. So you start with the Wildhausen K-theory. So how does Wildhausen, the simplicial object S dot, start like? It starts with a point here. Then we have S1Z, which is Z. And then you have S2Z, which is really C to the delta 1, up to equivalence. And we have 3 maps, and so on and so forth. And what you can do here is you can just put the bar construction of C in. Let me maybe put twiddles everywhere. So what you can do is here, you can do the bar construction of C with respect to direct sum. So the bar construction of the E-infinity monoid C. So you would have here C cross C, and so on and so forth. And then the claim is there's a map like this. And how does this map go? Well, here it sends X to X. And what does it do here? It will send X comma Y to the arrow, which is X to X wedge Y. And so on and so forth. And you can make this into a map of simplicial objects. In fact, a map of simplicial E-infinity monoids, and then you realize. So what does this give you after realization? It gives you a map from omega B C tilde into Wildhausen, omega infinity KZ. And of course, this is just a model, as I mentioned in the first lecture, of the group completion. In particular, there's a map like this. In fact, we see a little bit more. This is, in fact, the group completion of the underlying E-infinity monoid of a Wildhausen category, which is E-infinity by means of the direct sum, the coproduct. Okay, that's the way you get a functor like this. And in fact, of course, if you just had a functor like this, by the fact this is group-like, we could have already deduced the factors over the group completion. Okay, so that's a little construction. So, good. And well, of course, in order to make this totally precise, you have to be a little more careful than I'm here. But this gives us a map, and so here's the theorem. So first, Wildhausen proves what is called additivity. So it says that the map from C cross C to S2C, which we said was just C to the delta 1, which just takes X comma Y to the morphism X to X wedge Y. So this is in fact a functor of Wildhausen categories, and the claim is induces an equivalence KZ cross KZ. So in fact, Wildhausen K-theory of a product is easy to see to be the product of the Wildhausen K-theories, and then it has a map into K S2C. So S2C is it's a Waldhausen category in its own right. Not going to spell that out, but it's not super hard to give this a Waldhausen structure. It's not, I mean, the first guess is not right, but the second. So, and then that's additivity. So what does this say morally? This morally says that Waldhausen K-theory splits co-fiber sequences. Right, it morally tells me, in fact, you can even write down an inverse of this map, and this would be given by sending a map x to y to x, comma, the co-fiber of the map. So in Waldhausen K-theory, every sequence, every morphism looks like it's of this split form. That's what Waldhausen K-theory does. And then there's this beautiful theorem due to Barwick in this language, which says, in fact, Waldhausen K-theory is universal with respect to this functor. K-theory is universal with respect to 1. More precisely, the transformation from C tilde into, well, I guess omega infinity kz as functors, say, from Waldhausen infinity categories into E infinity monoids is initial among all functors out of C tilde that satisfy, whose target satisfies additivity. Oh, satisfies additivity. Okay, and maybe I should say n is product preserving. Okay, so this tells us precisely that Waldhausen K-theory is universal with respect to that, but as a functor, it's a different level of universal property of saying for a concrete category there's a universal property for the K-theory spectrum, like we did for group completion. It's just a universal property for the full functor. And Clark proves this in a somewhat ingenious way. He invents this new category and observed that the S-dot construction is a suspension in this new category. And then he just observed that being additive means you're excisive, and then he uses Goodwilly's formula for the excisive approximation. And in fact, in Goodwilly's formula would have to do omega infinity of S-dot infinitely often iterated. By additivity, you only have to do that once. But I personally, there's a different proof of that in a slightly different generality given by Blumberg, Gebner, Tabuada. And they essentially just use that S-dot is like an idempotent. So what morally happens is like the S-dot construction is just something you can iterate. And additivity exactly tells me that iterating this doesn't change it. And you can use that to show that this construction, which takes one functor and does this S-dotty thing to it, is actually an idempotent on the category of functors. Then the local object, in other words, the Bose-Field localization, and the local objects are exactly the additive functors. Okay, so anyhow, that's the universal property of Waldhausen K-theory. And in fact, you can use that, leverage that to reproduce a lot of what I said. Like, for example, you can get ring structures on Waldhausen K-theory of like categories, Waldhausen categories which support sufficient tensor products. Or you can, in fact, retranslate that story about lambda rings that I made, about polynomial functoriality into Waldhausen. Actually, I don't know that you can do it in Waldhausen categories, but for stable infinity categories, you can do that. So a lot of the story that somehow we did could be paralleled. But one thing I want to do now is I want to define if for R a ring spectrum. So, so far I've always assumed that if R was a ring spectrum, it's connective, but now I don't. So I want to define a stable infinity category as the subcategory of all module spectra. It's the smallest stable subcategory. Category obtained, which is closed under retracts and contains R. Okay, that's what a perfect module is. And equivalently, you could say it's a compact object in the category of modules over R. Or you could also say if R is commutative, it's a dualizable object. All these things are equivalent. But I like this definition because this exactly tells me what I should think about it. Because somehow it tells me you start with R, then you take direct sums and retracts of that. That's what we called projective before. And then I have to take cofibers and cones and stuff like that. So really I'm saying like everything in here by definition can be broken up to the expense of like cofiber sequence to projective modules. And that's really why this has to do in the case that you are actually connective, how you can compare that to actual K-theory as defined in terms of group completion before. And that's the next theorem. And that's theorem of Gillet-Waldhausen. And in fact, of course, maybe I should say, this is an ordinary ring. This is just the classical, or the infinity enhancement of the classical derived category of perfect complexes, i.e. complexes which are quasi-isomorphic to complexes that are of finite length and finitely generated projective in every degree. Okay, so here's the theorem, Gillet-Waldhausen. Well, if R is a connective ring spectrum, then the maps from, I mean, what can we do to a connective ring spectrum? We can, I mean, let me just momentarily denote group completion K-theory with this upper GP. We can take this category of projective R modules that we've used before to define K-theory. That was our old efficient definition. And now the point is, by this construction over there, we have this map into the Waldhausen K-theory of this category of projective R modules, where I let this be like a Waldhausen category where I just say like the split monos are the cofibrations, right? And then this I can embed further into the stable infinity category perf R. And I guess here really it's clear that we take Waldhausen K-theory. Let me still denote that. And the claim is these are equivalences. All right. So this somehow tells us that that we get back our old K-theory, but now we can, for example, define it for arbitrary ring spectra, not only for projective connective ones. And let me say a few words about the idea of the proof. Maybe I just verbatim say a few words about this theorem first. I guess I've already explained roughly how to think of part 2 of the theorem. For part 1, you really end up contemplating this Siegel space that Toby has talked so much about. So really in this situation you're going to sort of translate that over into like a fiber sequence that you want to prove, where you go from C to S2C and then down to C back, with taking C to the identity and then with the cofiber. So you have to prove this is a fiber sequence. And then it's not hard to see that on S dot, which is a simplicial space, this is level-wise a fiber sequence. So what you end up proving is you have a level-wise fiber sequence of simplicial spaces, and it stays a fiber sequence after geometric realization. So it's a sort of fibration in the category of simplicial spaces. Like that's what Resk calls the realization fibration. And then you have to work and show that this is actually true. So that's quite a bit of work, but can be done. Okay, that's roughly how you prove this. And yeah, 2 I already said. 3, which doesn't have a number, but is secretly 3, consists really of 2 theorems. First theorem is whenever you're in a situation of a Waldhausen category where every cofibration splits, the inclusion from the group completion into the Waldhausen K-theory is an equivalence. And well, this actually just proved by, I mean, this comes down to proving something about the construction which I just erased, about this map. You just essentially prove that it's level-wise an equivalence after group completion, and that is essentially equivalent to proving an additivity style result for group completion K-theory. And that can be done relatively explicitly. You just essentially say, if I do group completion K-theory of this upper map, then it's also like an equivalence, essentially. And in the split situation, you can, I mean, it's not quite true that you can write down an inverse. If everything splitted canonically, you could write down an inverse. So the kind of trick is to add onto enough factors that up to a group completion, you can essentially do that argument. I mean, this is a very rough sketch, but. And so let me say a few words about the very last theorem, namely that this is an equivalence. So I already essentially explained the pi naught version to you. On pi naught, you would just say everything can be broken up into projective modules. So up to like shifting and stuff like that, it's okay. It's at least surjective, the map. I guess that's what this argument really shows, that the map is surjective. And if you want to prove the actual theorem, the idea is as follows. Let's for simplicity assume R is an ordinary ring. So what you do is the following. So then we're going to contemplate this category of perfect R modules. Let me denote it like that. It's really perf R in my notation from before. I'm just sticking to the more classical notation, the derived category of perfect objects. And this is a stable infinity category. And the point is, then you're going to compare that with an actual, and let me, despite my usual habits, write the nerve of an actual one category, which is really the category of projective, chain complexes, bounded chain complexes of projective modules. So that's really one category. Don't invert any quasi-iso, anything like that. It's a one category. And then actually you have those projective modules which are acyclic. So that's, to me really funny that you actually want to learn something about this infinity category and you compare it with this funny one categories. But anyhow, this is how the proof goes. And then, there's a theorem by Waldhausen. It's the fibration theorem. This induces a fiber sequence in K-theory. I don't want to comment on that. It's roughly has a similar proof to one, or it follows from one through some sort of funny descriptions. But so this tells us it's actually a fiber sequence in K-theory, where this guy is actually considered to be a Waldhausen category, where you just do the level-wise monos, I guess. So that the co-fiber again is in here. And then by induction, you can also prove induction using additivity. You prove that K-theory of the left-hand guy is an infinite sum of KRs. And the same of the middle guy, middle, it's also a direct sum of KRs. Well, this is basically clear because just using, a chain complex you can just break up into its layers because it's level-wise projective, and then using additivity you just see it's like equivalent to the K-theory of all just the layers. And the same is true here, but this is somehow one factor less than here. Okay, both are countable, so this doesn't make sense, but if you say chain complex is concentrated in a fixed range, then you get only finitely many factors, and here one less. So as a result, the co-fiber is just one copy of K of R, and this remains in the co-limit. Okay, and that's how you prove it. So I just wanted to mention that, in fact, actually, this is true more generally, this fact that you can compare Waldhausen K-theory of some one category like Broch R and Waldhausen K-theory of an infinity category. That's kind of true in the generality of weight structures. And I think this has been worked out by a student of Andrews. His name is Fontes. He proves what he calls the weighty theorem of the heart. It's just, weight structure is roughly like a stable infinity category where you have something like the cell decomposition. It's weaker than a T structure. You don't have like canonical decompositions, but you somehow can start counting off bottom cells. Okay, good. That's what I wanted to say about this abstract situation. And so now let me draw a picture. So this is Waldhausen infinity categories. And this is symmetric monoidal infinity categories. Right, and there's an intersection. What is the intersection? It's essentially those Waldhausen infinity categories where every cofibration is split. Like objects like Proch R are in this intersection here. right? And so, I mean, we're very fortunate that those objects we care about actually lie in these intersections. So we have two tools available to compute its K-theory, either through this group completion thing, and the cool thing is in the group completion world you can compare that to other objects, like, for example, this category that I called vect C top. And note this category vect C top is actually a symmetric monoidal category and does not come from any sort of Waldhausen category. So it's very important. You cannot, I mean, at least not like a priori define topological K-theory as Waldhausen K-theory of something. I mean, you can a posteriori with a bunch of tricks, but not like directly. Right, so the point was that in this category was essentially the disjoint union of the BUNs. But this is not sitting as an infinity category as a groupoid core in some category which has cofibrations. And this is true as a one category if you consider it as a topologically enriched category. But if I consider it as an infinity category with a topology, then all the mapping space become contractible. Right? And on the other hand, we can relate this now here to other objects like perf R. And it's the same here. And so the purpose of today's lecture is to explain what tools we have here. And these are really localization tools which we have already like implicitly used. So I'm just saying, like, sometimes people say Waldhausen K-theory is the most general form of K-theory. This is not true because it does not cover all cases of group completion K-theory. So in some sense, this is like the high-fledged generalization of Quillen's Q construction, and this is like the high-fledged generalization of Quillen's plus construction. At the end of the day, you really need both to get information about K-theory. Okay, and Quillen already had both. That's the amazing thing. Okay, good. Right, so, and now let me say a word about, I mean, I guess is there a question? Sorry?
There's a semi-topological K-theory approach.
Right, so, you know, I'm not claiming that this picture covers the whole of K-theory, what people do in K-theory. But semi-topological K-theory, in some sense, just glues in the topological part from vect C top. You somehow externally need to define that beforehand, and then by a Kahn extension you glue it in. So I guess you could pretend that we know topological K-theory from some different source, and then we're fine. And so I guess this, yeah. I'm not claiming that you cannot really. I guess you can with some tricks also get an object in this Fizzle-derived category of Clark, which computes topological K-theory, or you could use the Karoubi conjecture to realize that topological K-theory is K-theory of this algebraic K-theory of the C-star algebra of compact operators. But you know, I'm just saying, like, most naturally, and I mean, or let me rephrase what I want to say. The rephrasing is there's no a priori way of getting handle on the homology of Waldhausen K-theory. So if we want to understand the homology of Waldhausen K-theory, we really want to use some sort of group completion technology. Maybe that's sort of a better way of phrasing what I want to say. Okay, so now I guess I already sneaked in this fibration theorem of Waldhausen's. And I mean, that's a general statement of this fibration theorem, but I personally find this most cleanest expressed in the language of stable infinity category. So let me do that, because this is a very important theorem, like generalizing or like maybe giving an analog of Quillen's localization theorem. So a sequence of stable infinity categories and exact functors C, D, E is called Verdier sequence, and this is a notion stolen from the theory of triangulated categories. If, well, I mean, one way if it is a fiber and cofiber sequence. Cofiber sequence in the category of stable infinity categories and exact functors. So what does this mean? This means the following. First of all, P after I is 0. And that's a property. This is not, we don't have to fix any choice of null homotopy. This is just saying for every object here, the resulting object here is 0. Secondly, C is the kernel of P, which is a full subcategory of D. So these exactly consists of all the objects which go to 0 here. And I guess in Emily's terms, if I say equal, it would be evil, so I should maybe say the inclusion of C into the kernel is an equivalence. It really means, essentially, it is the kernel. And 3 is, E is obtained from C, from D, by killing C. Killing C. In fact, this is just expressing it's a cofiber. Functors out of E are the same as functors out of D, which sends Z to 0. But more concretely, it's i.e. the Dwyer-Kahn localization, so the localization at a class of weak equivalences at maps f d to d prime such that fiber f lies in C. Right, I just declare all maps whose fiber or equivalently cofiber lies in C to be weak equivalences, and then I localize at those. And that's what E is. Okay, and in fact you can be fairly concrete about E. You can actually give a formula for the mapping spaces and stuff like that. Okay, good. That's the notion of a Verdier sequence. And there's a slight elaboration on that which is necessary in practice, which is the following notion. Such a sequence is exact. It's called exact sequence, to follow the notation of Blumberg-Gepner-Tabuada, if it is Verdier up to idempotent completion. Or if it is, let me say, if it is a fiber sequence, say, and the map from the abstract cofiber D mod C into E is an equivalence after idempotent completion. After idempotent completion. In other words, it's still fully faithful, but every object in here might only be a retract. So, this for a Verdier sequence, you see the functor from D to E is essentially surjective because, well, I just, for example, declared it to be a Dwyer-Kahn localization. And here I'm saying it's not quite essentially surjective, but almost. Non-surjective in a controlled way. Okay, so what are examples? Well, there's a bunch of obvious examples, like, for example, well, I guess we have C to C plus C to C. And I just write plus for the product of the two stable infinity categories, and I write plus because this happens to be a pre-additive infinity category. It's also the co-product. So that's an example, or the second example is related to the additivity theorem. It's just given by this sequence where you say this is maybe sent C to the identity, right? An object goes to the arrow which is the identity on that object, and then here you take the cofiber. It's also not hard to be a Verdier sequence, and in fact these are both like split Verdier sequences where this functor has an adjoint. But in general, a Verdier sequence doesn't have to be of this form, and that's maybe the most important case, and I think in some sense the case from a point of view of K-theory, which is why this plays an important role. So if R is a ring spectrum and X is an element in homotopy of R, and let's say this is central, right? For example, if R is a commutative ring spectrum, or in fact I could say here it satisfies an ORA condition, but let's say it's central, then we can consider perf R. And then actually we can localize the ring spectrum at that element and consider perf Rx to the -1. Right? So this functor is just given by base changing. In other words, you just take a module and invert this element X in this module. And the point is, it's not clear. This is why I needed to introduce this notion of exactness, because a priori it's not clear that every module here arises in this way. But up to idempotent completion it does. That's the point why I had to invent this notion of perfect things. And then what is the fiber of that? This is going to be perfect modules on R, which are 0 here. But what does it mean to be 0 here? This means if I invert X, it's 0. That means X acts nilpotently on homotopy. Well, that's kind of perf Rx nil. Okay, good. So that's a Verdier sequence. And that's kind of the one we care about today. Right, and in fact, actually you can sort of understand this term a little more explicit, maybe. This is what when Antio, Bartel and Gepner, Toby Bartel and David Gepner have done. I mean, I guess it's not so hard to see that this is true, but they really make efficient use of this fact that perf x nil is actually itself perf A, where A is just given by endomorphisms of R modules of R mod x. So you can just take the cofiber of R by x, and then you take endomorphisms of this as an R module. So if x is like a regular element, this looks like a two-term thing. So it's a ring spectrum, and somehow has two cells of the form R mod x, one in degree 0 and one typically in like negative degree. So in some sense, we can think of this term as corresponding to this kind of ring spectra, but in practice we somehow would like to get rid of that bottom cell. And that's what the visage theorems will sometimes allow us to do. And sometimes not. That's actually what they show here. But let me comment on that in a second. Okay. Right. Where did I put the eraser? And so what's the significance of these Verdier sequences for K-theory? And so that's a theorem, and I'm not entirely sure to whom to attribute this. This follows fairly directly from the Waldhausen fibration theorem, but I think let me say Thomasson, because I think he was the one to realize the importance. But I guess Marco Schlichting has worked a lot. I mean, Clark has a version of that, Blumberg, Ebner, Taboada. So let me not try to be fair here, because I don't think I can. So for an exact sequence CDE, there is an induced fiber sequence of connective spectra, KD, KE, like that. And why am I underlying connective? Because connective, the word connective modifies what fiber sequence means. Being a fiber sequence in connective spectra means it does not have to be surjective on pi naught here, right? The map from K naught D to K naught E does not have to be surjective. Right? So this is what a fiber sequence of spectra is, but it is connective. It is a fiber sequence of spectra, if the sequence was Verdier. Right, so you see exactly like the thing, for example, in this situation can come up that not necessarily every object here will come from here, but up to idempotent completion. It's still okay. Okay, good. And in fact, something I will not mention today for the lack of time is the fact that this is not surjective in K naught has actually the consequence that I can universally try to make it into a fiber sequence. I can sort of further force my functor to send this to fiber sequences, and this will create negative homotopy groups. That's how negative K-theory comes along. Then you get non-connective K-theory, sort of the sequence extends. You can sort of do that in a universal way. And that's actually what a lot of people have studied. And I mean, it can be obtained equally like universally, but I'm not going to touch upon that topic today. Okay, good. So that's a theorem. And before I sort of run some examples, let me first state some abstract consequences. Or maybe I can just sort of squeeze that in here. So the first consequence of that, and this is I think why Thomasson really cared, is that the assignment, the functor, which sends a ring to Kr, considered as an object in connective spectra, satisfies Zariski descent. You know, Zariski open sets are essentially these localizations, and so you can use these fiber sequences to prove that this functor satisfies Zariski descent. And so far I guess I've only talked about rings and ring spectra, But now we can talk about schemes. For example, if X is a scheme, I can now define K of X just to be the Zariski sheafification of this sheaf K. Right, the global sections of that sheaf. And I guess I could have made this definition before, but before this could have potentially changed the value on affines. But now this theorem tells me it doesn't. And really, this is maybe not the best official definition of K-theory of a scheme. So in fact, you can also define K-theory of a scheme directly as K-theory of perfect complexes on that scheme. But then you have to be very careful what exactly the perfect derived category of that scheme is. So it's not true in general that you can represent that by means of just chain complexes of vector bundles. For that you need something like an ample line bundle or family of ample line bundles. And even if I think in generality you can't even represent that by OX modules. You can if you're like quasi-compact, quasi-separated. I mean, my definition is the following. My favorite definition is the following. You just say what it is for affines, which I just did over there, and then you Zariski sheafify as a sheaf of categories. And then this verbatim makes this true by definition, but of course, then you have to say what that means. I mean, like, I guess abstractly it's clear, but in practice you want to sort of maybe name elements in there. And that might be hard in abstract sheafification of a sheaf of categories.
K of Prof X is okay the way you define Prof X, if you do it as some ends of a structure sheaf and stuff. It's bad if you use compact objects, but that's fine.
Like in general? I mean...
Yeah, it's fine you don't need quasi-compact, quasi-separated.
Well,
compact, quasi-separated lets you use compact objects.
No, I mean, this is not true. No, not in that generality. I mean, it's not compact objects in that generality, no.
Were you also saying that even this perfectness definition where you ask Zariski locally quasi-isomorphic to bounded complex, that's not...
Right, but first of all you have to say what object is Zariski locally quasi-isomorphic, right? First you have to say a certain object which is Zariski locally quasi-isomorphic, yes, and then you first have to tell me what that object is. And you could sort of ask it to be a complex of quasi-coherent sheaves, but that's not good. And then you could ask it to be a complex of OX modules, just sheaves on the underlying space, and that's better, but also I think, I mean, maybe Harry is just claiming the opposite, but I think this is not true in generality, that this is good enough. But I might be wrong. Actually, that's actually a long discussion in EGA about notions of perfect complexes, and also a long discussion in the appendix of the Thomasson-Troubaud paper. And I'm like, periodically panic about that when I look it up. So actually, I really prefer this sheafify the sheaf of categories. Okay, good. So, good, but the one thing is, but there's no étale descent. And so K-theory doesn't satisfy étale descent, so as a result I can just make it do that. And that's what's called étale K-theory. That would just be the étale sheafification of X with values in K. And let me just say this is the étale Postnikov sheafification without commenting further on that. So this is a sheaf of spectra, and for sheaves of spectra there's different, I mean the toppers of the étale toppers is not hypercomplete. As a result, there are different things that sheafification might mean, like hypersheafification, Postnikov sheafification, or just sheafification. That's, I think, one of the insights of Jacob Lurie in higher topo theory, that somehow beforehand people would always consider the hypersheafification, and Jacob sort of realized that there are different notions you could do, and I think what Thomasson did is the Postnikov sheafification. Anyhow, let's gloss over this point and just say that we have already understood what the stalks are. If L is invertible on X, then actually last time I told you what K-theory of algebraically closed fields is, and really what I should have said is like K-theory of strictly Henselian local rings, because that's the generality in which this Gabor result really tells us what that is. And this was essentially a form of KU, right? So essentially we totally know what the stalks of this, I mean, like the toppers points of the étale toppers are exactly these strictly Henselian local rings, so we totally understand the stalks of that sheaf. So in some sense this tells me that this étale K-theory can be entirely understood. I mean, I guess because I'm working connective, let me say connective cover of something like x to the little ku. And I'm L completing. And so what do I mean by that? So say if x is like a smooth variety over the complex numbers, then this would just be the underlying space. And that would just be the ku cohomology of that space, where I'm slightly lying here. Really, this is a local system of ku modules. But it comes pull back.
Ku to the x when you said it.
Yeah, sorry, ku to the x. Absolutely. So there's a local system of ku modules on that space, but it's like very mildly non-constant. It just comes from pi 1. So that's just the Tate twist, which tells me how non-trivial this is. And in general, I guess x means the étale homotopy type. So you always have the sheaf of ku modules on the étale homotopy type, and you just take global sections of that. So in fact, this gives you a spectral sequence from étale cohomology to étale K-theory. And that's how it's in practice computed. Okay, and I put quotation marks. You have to interpret the statement correctly. And really, what you want to do is you don't want to take connective cover, so you either want to work with non-connective K-theory or even better, invert the bot element. So by invert the bot element, I mean there's a sort of bot element once your ring has enough roots of unity. And if not, then inverting the bot element means K1 localization. But anyhow, so just take away, besides everything that's wrong that is stated here, the message. I mean, everyone has to formulate a message now. Now these days. So the message is that you can compute that in terms of actual, étale cohomology. That's the point. Okay, good. So, but this was just a little statement about étale K-theory, and this is only away from the characteristic. That's important here. So at the characteristic, you want to use trace methods. Okay, good. So good. So, but what did I say? So I guess I erased this fiber sequence, unfortunately. I had this fiber sequence where I said contemplate perfect modules over R, then modules over the localized ring, and then I had this nil term. And really what we want to have is understand this term perf x nil, or like what Thomason calls like x on z, if you think of z as the closed complement to the Zariski open set. And so this is the content of Devisage theorems. And here's one Devisage theorem, which is, I think, very beautiful and due to Clark. And I guess modeled on a theorem of Niemann, which says the following. So if C is a stable infinity category with a bounded T structure, so a bounded T structure is essentially something which tells you can formally form Postnikov towers. And it's bounded if these Postnikov towers are bounded. In other words, you can just take homotopy groups and Postnikov towers within your category, and the subquotients will lie in the heart. And the heart is an abelian category. So the statement is that then K-theory of C of the stable infinity category is equivalent to K-theory of this heart, which is an abelian category. That's the theorem, and it's just true in this generality. And let me explain how to use the theorem. So let me first start with an example for which this is somewhat overkill. But by definition, we already knew K of Broch C, where defined, say, as Waldhausen or group completion K-theory, was equivalent to K of perf C, perfect complexes. But the point is, perfect complexes itself has a T structure. If you just take a perfect complex over the integers and you brutally truncate it, you take the quotient. So the homology of a perfect complex is itself a finitely generated abelian group. It's a statement about the integers. This is not true in general over general rings, but over the integers is. And then you can just take this Postnikov tower, and so the heart is going to be exactly finitely generated abelian groups. This is equivalent to K-theory of finitely generated abelian groups. And this is true over every regular ring, actually. And in fact, this was known long before this. This has somehow the resolution property in the language of Quillen. But that's the statement. So we know that K-theory of this like Waldhausen category is just equivalent to K-theory of this abelian category. But more importantly, you can recover a theorem of Blumberg-Mendel, which is really cool, which says the following. So you want to compute K-theory. I mean, let's say we want to compute K-theory of topological K-theory, big Ku. And for some reason, we are able to compute K-theory of little Ku. For example, we use trace methods. Trace methods really work for connective ring spectra or these homology methods or anything like that. But big Ku is periodic. And then sort of we use this localization sequence to see that here we get K-theory of the category of perfect little Ku modules, which are nilpotent with respect to the bot element. Right, that's what this is, localization at a bot element. So these are, and so what's the point? Point is if you have something which is beta nilpotent, then it has to be bounded. Right, so if you have a perfect module over Ku and beta acts nilpotently, then it's bounded in homotopy. This is not true if I just said perfect, because Ku is an example of a Ku module, but if it's beta nilpotent, then it's bounded. So as a result, you just have a bounded T-structure. Just the usual T-structure works. It's bounded. It wouldn't be bounded here, but it's exactly bounded here. So as a result, what is the heart of this T-structure? I just do ordinary Postnikov towers. Well, then I have a Ku module which just sits in degree 0. There's nothing of the Ku action left. It's just a finitely generated abelian group. This is just the same as finitely generated abelian groups. And that's just K of Z by what we've seen above. So that's the fiber sequence relating K of Z, and this is Blumberg-Mendel's theorem. And in fact, I think they essentially give the proof of this theorem in that case. And then later, Clark generalized it. I mean, I don't want to comment on that. People are in the room. You should ask them. But I mean, it's a beautiful theorem, just this fiber sequence. And so let me also, of course, make the even more important case that Quillen already did of localization theorems. And for that, actually, we need the original theorem that Quillen proved. So what's the original de Visage theorem of Quillen? It says the following. So it says if A into B is an exact inclusion of abelian categories, say. And every object in B has a finite filtration whose subquotients lie in A. Then the inclusion induces an equivalence on K-theory spectra. And you see, these theorems are very, very similar in flavor. So here we say I have a bounded T-structure. In other words, everything has sort of a Postnikov tower, a filtration whose subquotients lie in the heart. And here I have this filtration where the subquotients lie in the smaller category. Right? But I mean, it turns out technically they are somehow totally different, unfortunately. But anyhow, so these theorems are both sort of de Visage style theorems. This is what's classically called de Visage, and that's the theorem of the heart. And let me also demonstrate this in like the most classical example of that. So say we want to understand K of the integers. And well, we can somehow understand this guy, because here the prime P is invertible, and I'm only working at finite primes. So rationally, rationally it's hard. You have to read Borel's paper. But at finite primes, I'm P completing at finite primes, and P is invertible. And we've just seen that we have methods, at least we can understand étale K-theory by means of these kind of methods that are sketched above, or maybe somewhere. Well, on the video, you can just turn back. It was here somewhere, I think. So, any case, so we have methods of understanding that, and really we have methods to understand étale K-theory, and I haven't explained how to exactly relate étale K-theory and K-theory, the subject of Quillen-Lichtenbaum and Bloch-Kado. And I'm not going to really, say a few words at the end, but there are methods of relating that. So in this case, in fact, it turns out it's an equivalence above degree 1. So maybe going to QP. So this we can somewhat understand. It's still hard, but we can understand that. So the statement is, a priori, from this abstract localization theorem, we get that this is somehow K-theory of the category of perfect complexes of Z modules whose homotopy is P nilpotent. Right, so P acts nilpotently on the homotopy. But that then is by sort of an abstract style theorem of weight nature equivalent to K-theory of just finitely generated modules which are P nilpotent. So that's now we're in the realm of abelian categories. And now we can actually sort of, being P nilpotent just means it's P power torsion. In other words, it just has a filtration whose subquotients are actually P torsion. But the filtration is just look at the elements which are actually P torsion, then the elements which are P squared torsion, P3, and so on and so forth. So that's the exact filtration you're going to use. And then classical equivalent de Visage tells us this is K of. And what is the subquotients like? They're actually just P torsion guys. In other words, FP vector spaces. So this is just K theory of FP. And that we can also understand. I guess I haven't really fully explained the computation of that, but that's classical. So in other words, if we want to understand K of the integers, what we really got to do is compute K theory of the rationals, if you want. I mean, like, we can do that for all primes at once, then we're content to computing K theory of the rationals. And that can be compared by Bloch-Kado or like by Quillen-Lichtenbaum to the étale K theory, where there stands a chance of computing that. So in other words, this translates it into a problem in étale cohomology. And that turns out to be a problem that has been almost solved, but in some degrees it's open. So that's the Van der Veer or Van Diver conjecture. But up to this conjecture, these methods let you entirely compute K theory of the integers. Okay, good. Let me end by a question and a little outlook. So here's a question. And this, I guess, is a question which a lot of people have asked. So the question is there a joint generalization of the last two theorems? Of the last two theorems. I mean the theorem of the heart and Quillen's de Visage. So I guess that's a question which has a lot of, attracted a lot of attention. I think Clark has some real good thoughts on this. So you should ask him. And I guess like John Rockness had some questions about, like, if you just assume there's such a sort of generalization, you can just look at certain fiber sequences of related to BP pointy brackets n, and wonder if these are fiber sequences, if you want to actually calculate K theory of these ring spectra. And then I guess in this language of this A module that I had, this two-cell complex, this somehow starts looking exactly like a de Visage question. You have this negative homotopy group, and you just want to de Visage that away. And so if you just formally do that, you can establish these fiber sequences. But then, I mean, be aware of the work of Antio, Bartel, and Gebner again. So what they do is they prove actually this can't work in this generality. You can't just always de Visage that away. So they explicitly use this perspective of having this A module, this module A, and then they use the Hochschild homology computation to prove that there can't be such a fiber sequence. So I'm just saying, I mean, I think this is a great question. I mean, it's probably hard. It's very hard. And the problem is mostly, I mean, for me the problem is, I mean, everything I can dream of, like being true, is immediately sort of false because of their work. So I wouldn't even know how a statement looks like, but it seems to me that this is like something that would be really nice to have. Okay, so now as a very last thing, I'm just going to tell you what I didn't cover in this course. Left out. And so shamefully admit that. So tools, so if you really want to learn about K-theory, and I think probably most of the people, many of the people here know way more than I about K-theory in this room. But let me just say, like, one of the big tools I didn't mention at all is motivic cohomology. So there's this whole world of motivic homotopy theory and motivic cohomology, which basically arose out of making motivic filtration on K-theory, whose subquotients are motivic cohomology. And so you get a spectral sequence from motivic cohomology to K-theory. And that's, for example, used to prove Quillen-Lichtenbaum, or like Bloch-Kado by Vygotsky. So this tells you something about that the map from K-theory to étale K-theory is actually an isomorphism in high enough degree, so above the dimension. That's what the Quillen-Lichtenbaum conjecture is, and that's kind of by this motivic methods you can see that. So in fact, this is maybe the most important technique which I sort of didn't say any word about. The second thing is recently there's this brilliant work on CDH descent and the Weibel conjecture. So conjecture by, which was proven by Kurtz, Kammer, and Strunk. So what is CDH descent? CDH descent is essentially saying that K-theory satisfies some sort of descent, in fact pro-CDH descent for certain abstract blow-up squares. So if you have something like a singular scheme and you try to blow up certain singularities, you want to see what this does in K-theory. And they tell us one can. And so Weibel's conjecture is that if you have such a scheme, which is nice enough, but it can be singular, and then it says that the negative K-theory, which I haven't defined, only reaches down to the dimension of the ring, the Gruel dimension of your guy. In other words, the singularities can't be too bad. It's a little bit like in topology, right? If we just look at the CW complex of dimension n, it doesn't have to be a manifold. Nevertheless, we can just compute its little ku homology, and this will only go down to dimension minus n. And this is somehow a sort of algebraic K-theory version of that, which was open for quite a number of years and was brilliantly resolved. And so the third left out is one of the things I stressed in my first lecture was that this algebraic K-theory of spaces and algebraic K-theory in general is very important in geometric topology. And so the most important thing in related to K-theory is like the Farrell-Jones conjectures. Farrell-Jones conjecture. So this is about understanding K-theory of group rings, where G is a group and typically non-finite. This is sort of the fundamental group of a manifold, or maybe better, even A theory of the K-theory of the spherical group ring. And somehow the Farrell-Jones conjecture tells me that I can break this K-theory of a group up into smaller pieces, like K-theory of subgroups, which I can understand, virtually cyclic subgroups, precisely. And so you somehow pretend that you understand K-theory of those, and then you sort of can write K-theory of the big thing as a big homotopy co-limit of those. For example, if this is true for the group G, this immediately implies the Borel conjecture. Borel conjecture is the following conjecture. You have two aspherical manifolds, in other words, manifolds which are KG1s, and they are homotopy equivalent, which just means the fundamental groups are isomorphic. Then it implies that they are already homeomorphic, the manifolds. It's a super strong rigidity result and really follows from, actually it follows from an L-theoretic version of that, but let me not comment on that by surgery. So that's a very important field in algebraic K-theory that a lot of people work on. Then another thing I didn't mention at all is excision. So K-theory in low degrees satisfies excision for so-called Milnor squares, and you can actually wonder what happens in higher degrees. And in fact, it's a theorem of Suslin that there's still, if you're in a so-called Tor unital situation, then you still have excision. And this is related to the Karoubi conjecture in C-star algebras. Or it immediately resolved the Karoubi conjecture. And there's this very beautiful treatment of Georg Tamme, who's just sort of, I always thought this is incomprehensible. For me, because I don't understand the techniques that were used by Suslin, this was somewhat incomprehensible. This is a statement about me, not about the way it's written up. But then Georg Tamme gave this brilliant proof just using Verdier sequences of stable infinity categories, which is really like a few pages, and you should really go read that. It's beautiful. With everything I told you, you can essentially understand that paper and just understand when. And actually, there's also a version related to my fifth point, which is actually a thing which is closest to my heart, is trace methods. So trace methods are the following idea. Well, I guess we saw that K-theory had some universal property. K-theory of a stable infinity category had this universal property, right? It was kind of the universal functor which was additive. So as a result, as soon as you come up with any other functor which produces spectra from stable infinity categories, and it's also additive, or maybe localizing, you immediately get a map. And so there are a bunch of these functors like THH, topological Hochschild homology, or better TC, which is a refinement of topological Hochschild homology. I mean, yeah, it's a fiber of two maps on the homotopy as one fixed points on topological Hochschild homology. And so this is somehow something which one can understand in some sense. And we have this map, and it's actually a theorem of many people that this is a good approximation, like Dundas, McCarthy, and recently there's a real nice theorem of Matthew that I will conclude with somehow. I mean, there's been some recent breakthroughs in TC, and I think this culminates in this beautiful theorem of Matthew, and I'm just thinking about the alphabetical order, Clausen. Oh, man. Let me put it here. Dustin Clausen, Akhil Matthew, and Matthew Morrow, which says essentially that for a p-adic ring, p-complete ring, p-adic K-theory is equivalent to TC. P-adic commutative ring, or more generally Henselian along P. I mean, and actually, no, sorry, I said it wrong. I should say étale K-theory. Okay, that's somehow.
What was the assumption?
R is the p-complete. I mean, should I say p-complete or Henselian along P? Do you care about Henselian rings which are not p-complete, Jesper? Okay. Say p-complete. And commutative. I mean, this is really like the work of many people. It's kind of based on work of Morrow and Dundas and Dundas McCarthy, and a lot of computations done by Geiser Levine and Geiser Hesselholt. But it's just as beautiful as it is. So this tells you actually, at the characteristic of your field, you really want to use these kind of methods to understand what's going on. So then you sort of can understand sort of the building blocks of this étale stuff, and then you can go from there. Okay, good. Thank you very much for listening through my 4 talks. And I mean, I actually wrote some notes about this lecture series in case you care. I just probably at some point upload them on my homepage. And yeah, thanks.
Wish list. For the notes.
Do the notes include the trace methods?
Right.
Well, yeah. I mean, you should really go read their paper about this result. And I've actually given lecture series about THH and TC before, and I've also written notes about that, which are also on my homepage. This is a separate set of lecture notes, or something like lectures on THH or something. And so these two, I mean, the problem is this doesn't cover K-theory. Now I cover K-theory. So there would have at some point to be a third lecture which makes the exact connection, but I think I'm really not the person to do that. That's really like someone like Björn or maybe Akhil or one of these authors should do that. Anyhow, so their paper is really well written. Particularly, I find this also a very good source if you want to understand this result of Gabber that I alluded to at the beginning, that somehow if you're Henselian and away from the characteristic, you have an equivalence. So really, I mean, I sort of alluded to that they really proved that this is true, that you don't have an equivalence, you don't assume L is invertible, but the difference is measured in TC. That's really the main theorem they proved. And so it includes this Gabber result, and so I find this a really, really great paper.
Thomas? When you say before that the block Kato makes a connection between K-theory and the étale version, I missed where there is this connection. I mean, I heard that somehow K-theory satisfies étale descent from a certain point.
That's what Grün-Lichtenbaum says. That's like the map from K-theory into étale K-theory is like an isomorphism in degrees above the dimension.
Okay.
And so, in some sense, this is really the question is how much étale descent does K-theory still satisfy in some sense. And so that's exactly what these like motivic methods let you figure out. But really, I'm not an expert on these motivic methods. It's really a whole field in its own right.
no more questions. Let's thank Thomas for his whole lecture.